The National Academy of Sciences has produced this video to help summarize what is known about climate change. What is climate? Climate is commonly thought of as the average weather conditions at a given location or region over time. People understand climate in many familiar ways. For example, we know that winter will generally be cooler than summer. We also know the climate in the Mojave Desert will be much different than the climate in Greenland. Climate is measured by statistics such as average temperatures and rainfall, and frequency of droughts. Climate change refers to changes in these statistics over seasons, and year-to-year changes as well as decades, over centuries, and even over thousands of years, as with how Earth moves in and out of ice ages and warm periods. This video is intended to help people understand what has been learned about climate change. Enormous inroads have been made in increasing our understanding of climate change and its causes, and a clearer picture of current and future impacts is emerging. Research is also shedding light on actions that might be taken to limit the magnitude of climate change or adapt to its impacts. We lay out the evidence that human activities, especially the burning of fossil fuels, are responsible for much of the warming and related changes being observed on Earth. The information is based on a number of National Research Council reports, each of which represents the consensus of experts who have reviewed hundreds of studies, describing many years of accumulating evidence. The overwhelming majority of climate scientists agree that human activities, especially the burning of fossil fuels, are responsible for most of the global warming being observed. But how was this conclusion reached? Climate science, like all science, is a process of collective learning that relies on the careful gathering and analysis of data, the formulation of hypotheses, and the development of computer models to help understand past and present change. It is the combined use of observations and models that help test scientific understanding in order to help predict future change. Scientific knowledge builds over time as new observations and data become available. Confidence in our understanding grows when independent global analysis by scientific groups in different countries show the same warming pattern, or if other explanations can be ruled out. In the case of climate change, scientists have understood for more than a century that emissions from the burning of fossil fuels should lead to an increase in the Earth's average surface temperature. Decades of observations and research have confirmed and extended this understanding. How do we know that Earth is warmed? Scientists have been taking widespread global measurements of Earth's surface temperature for centuries. By the 1880s, there was enough data to produce reliable estimates of global average temperature. These data have steadily improved, and today, temperatures are recorded by thermometers at many thousands of locations, both on land and over the oceans. Different research groups, including NASA's Goddard Institute for Space Studies, Great Britain's Hadley Center, and the Japanese Meteorological Agency, have used these raw measurements to produce records of long-term surface temperature change. Research groups work carefully to make sure the data aren't skewed by such things as changes in the instruments taking the measurements, or by other factors that affect local temperature, such as additional heat that has come from the gradual growth of cities. These analyses all show that Earth's average surface temperature has increased by more than 1.4 degrees Fahrenheit over the past 100 years. With much of this increase taking place over the past 35 years. A temperature change of 1.4 degrees Fahrenheit may not seem like much if you're thinking about a daily or seasonal fluctuation. However, it is a significant change when you think about a permanent increase averaged across the entire planet. For example, 1.4 degrees is more than the average annual temperature difference between Washington, D.C. and Charleston, South Carolina, which is more than 450 miles south of Washington. Think about this. On any given day, a difference of 9 degrees Fahrenheit might be the difference between wearing a sweater or not, but a change of 9 degrees in the global average temperature is the estimated difference between the climate of today and an ice age. In addition to surface temperature, other parts of the climate system are also being monitored carefully. For example, a variety of instruments are used to measure temperature, salinity, and currents beneath the ocean surface. Weather balloons are used to probe the temperature, humidity, and winds in the atmosphere. A key breakthrough in the ability to track global environmental changes began in the 1970s with the dawn of the era of satellite remote sensing. Many different types of sensors, carried on many dozens of satellites, have allowed us to build a truly global picture of changes in the temperature of the atmosphere and of the ocean and land surfaces. Satellite data are also used to study shifts in precipitation and changes in land cover. Even though satellites do not measure temperature in the same way as instruments on the surface of Earth, and any errors would be of a completely different nature, the two records agree. A number of other indicators of global warming have also been observed. For example, heat waves are becoming more frequent. Cold snaps are now shorter and milder. Snow and ice cover are decreasing in the northern hemisphere. Glaciers and ice caps around the world are melting. And many plant and animal species are moving to different latitudes or higher altitudes due to changes in temperature. The picture that emerges from all of these data sets is clear and consistent. Earth is warming. How do we know that greenhouse gases lead to warming? As early as the 1820s, scientists began to appreciate the importance of certain gases in regulating the temperature of Earth. Greenhouse gases, which include water vapor, carbon dioxide, methane, and nitrous oxide, act like a blanket covering the Earth, trapping heat in the lower atmosphere, known as the troposphere. Although greenhouse gases are only a tiny fraction of Earth's atmosphere, they are critical for keeping the planet warm enough to support life as we know it. Here's how the greenhouse effect works. As the sun's energy hits Earth, some of it is reflected back to space, but most of it is absorbed by land and oceans. This absorbed energy is then radiated upward from the surface of Earth in the form of heat. In the absence of greenhouse gases, this heat would simply escape to space, and the planet's average surface temperature would be well below freezing. But greenhouse gases absorb and redirect some of this energy downward, keeping heat near the surface of Earth. As concentrations of heat-trapping greenhouse gases increase in the atmosphere, Earth's natural greenhouse effect is amplified, like having a thicker blanket, and surface temperatures slowly rise. Reducing the levels of greenhouse gases in the atmosphere would cause a decrease in surface temperature. How do we know humans are causing greenhouse gas concentrations to increase? Determining the human influence of greenhouse gas concentrations was challenging because many greenhouse gases occur naturally in Earth's atmosphere. Carbon dioxide is produced and consumed in many natural processes that are part of the carbon cycle. Once humans began digging up long-buried forms of carbon, such as coal and oil, and burning them for energy, additional CO2 was released into the atmosphere, much more rapidly than in the natural carbon cycle. Other human activities, such as cement production and cutting down forests, have also added CO2 to the atmosphere. Until the 1950s, many scientists thought the oceans would absorb most of the excess CO2 released by human activities. Then, a series of scientific papers were published that examined the dynamics of carbon dioxide exchange between the ocean and atmosphere. including a paper by oceanographers Roger Revelle and Hans Suess in 1957, and another by Bert Bolin and Erik Erikson in 1959. This work led scientists to the hypothesis that the oceans could not absorb all of the CO2 being emitted. To test this hypothesis, Revelle's colleague Charles David Keeling began collecting air samples at the Mauna Loa Observatory in Hawaii to track changes in CO2 concentrations. Today, such measurements are made at many sites around the world. The data reveal a steady increase in atmospheric CO2. To determine how CO2 concentration varied prior to modern measurements, scientists have studied the composition of air bubbles trapped in ice cores extracted from Greenland and Antarctica. These data show that for at least 2,000 years before the Industrial Revolution, atmospheric CO2 concentration was steady, and then began to rise sharply beginning in the late 19th century. Today, atmospheric CO2 concentration exceeds 390 parts per million, around 40% higher than pre-industrial levels. And according to ice core data, higher than any point in the past 800,000 years. Human activities have increased the atmospheric concentrations of other important greenhouse gases as well. Methane, which is produced by the burning of fossil fuels, the raising of livestock, the decay of landfill wastes, the production and transport of natural gas, and other activities increased sharply throughout the industrial age, before starting to level off at about 2.5 times its pre-industrial level. Nitrous oxide has increased by roughly 15% since 1750, mainly as a result of agricultural fertilizer use, but also from fossil fuel burning and certain industrial processes. Some industrial chemicals, such as chlorofluorocarbons, used in refrigerants and spray cans, act as potent greenhouse gases and are long-lived in the atmosphere. However, the concentration of CFCs are decreasing due to the success of the 1989 Montreal Protocol, which banned their use. Because CFCs do not have natural sources, their increases can easily be attributed to human activities. In addition to direct measurements of atmospheric CO2 concentrations, there are detailed records of how much coal, oil, and natural gas is burned each year. Through science, estimates are made of how much CO2 is being absorbed on average by the oceans and plant life on land. These analyses show that almost half of the excess CO2 emitted from human activity remains in the atmosphere for many centuries. Just as a sink will fill up if water enters faster than it can drain, human production of CO2 is outstripping Earth's natural ability to remove it from the air. As a result, atmospheric CO2 levels are increasing. A forensic-style analysis of the CO2 in the atmosphere reveals the chemical fingerprints of natural and fossil fuel carbon. These lines of evidence prove conclusively that the increase in atmospheric CO2 is the result of human activities. How much are human activities heating Earth? Greenhouse gases are referred to as forcing agents because of their ability to change the planet's energy balance. A forcing agent can push Earth's temperature up or down. Greenhouse gases differ in their forcing power. For example, a single methane molecule has about 25 times the warming power of a single CO2 molecule. However, methane has a shorter lifetime in the atmosphere and is less abundant, while CO2 has a larger warming effect because it is much more abundant and stays in the atmosphere for much longer periods of time. Scientists can calculate the forcing power of greenhouse gases based on the changes in their concentrations over time, and on physically based calculations of how they transfer energy through the atmosphere. Some forcing agents push Earth's energy balance toward cooling, offsetting some of the heating associated with greenhouse gases. For example, some aerosols, which are tiny liquid or solid particles, such as sea spray or visible air pollution suspended in the atmosphere, have a cooling effect because they scatter a portion of incoming sunlight back into space. Human activities, especially the burning of fossil fuels, have increased the number of aerosol particles in the atmosphere, particularly over and around major urban and industrial areas. Changes in land use and land cover are another way that human activities are influencing Earth's climate. And deforestation is responsible for 10 to 20% of the excess CO2 emitted to the atmosphere. As mentioned previously, agriculture contributes nitrous oxide and methane. Changes in land use and land cover also modify the reflectivity of Earth's surface. The more reflective a surface, the more sunlight is sent back to space. Cropland is generally more reflective than undisturbed forest, while urban areas often reflect less energy than undisturbed land. Globally, human land use changes have had a slight cooling effect. When all human and natural forcing agents are considered together, scientists have calculated that the net change in climate forcing between 1750 and 2005 is pushing Earth toward warming. The extra energy is about 1.6 watts per square meter on the surface of Earth. When multiplied by the total surface area of Earth, this represents more than 800 trillion watts of energy. This energy is being added to Earth's climate system every second of every day. That means each year we add to the climate system more than 50 times the amount of power produced annually by all the power plants of the world combined. The total amount of warming that will occur in response to a climate forcing is determined by a variety of feedbacks, which either amplify or dampen the initial change. For example, as Earth warms, polar snow and ice melt away, allowing the darker colored land and oceans to absorb more heat, causing Earth to become even warmer, which leads to more snow and ice melt, and so on. Another important feedback involves water vapor. The amount of water vapor in the atmosphere increases as the ocean surface and the lower atmosphere warm up. Warming of 1 degree Celsius, or 1.8 degrees Fahrenheit, increases water vapor by about 7%. Because water vapor is also a greenhouse gas, this increase causes additional warming. Feedbacks that reinforce the initial climate forcing are referred to in the scientific community as positive or amplifying feedbacks. There is an inherent lag time in the warming caused by a given forcing. This lag occurs because it takes time for parts of the Earth's climate system, especially the massive oceans, to warm or cool. Even if by magic we could hold all human-produced forcing agents at present-day values, Earth would continue to warm well beyond the 1.4 degrees Fahrenheit already observed because of human emissions to date. How do we know the current warming trend isn't caused by the sun? Another way to test a scientific theory is to investigate alternative explanations. Because the sun's output has a strong influence on Earth's temperature, scientists have examined records of solar activity to determine if changes in solar output might be responsible for the observed global warming trend. The most direct measurements of solar output are satellite readings, which have been available since 1979. These satellite records show that the sun's output has not shown a net increase during the past 30 years, and thus cannot be responsible for the global warming during that period. Before satellites, solar energy had to be estimated by more indirect methods, such as records of the number of sunspots observed each year, which is an indicator of solar activity. These indirect methods suggest there was a slight increase in solar energy during the first half of the 20th century, and a decrease in the latter half. The increase may have contributed to warming in the first half of the century, but that does not explain warming in the latter part of the century. Further evidence that current warming is not a result of solar changes can be found in the temperature trends in the different layers of the atmosphere. These data come from two sources: weather balloons, which have been launched twice daily from hundreds of sites around the world since the late 1950s, and satellites, which have monitored the temperature of different layers of the atmosphere since the late 1970s. Both of these data sets have been heavily scrutinized, and both show a warming trend in the lower layer of the atmosphere, the troposphere, and a cooling trend in the upper layer, the stratosphere. This is exactly the vertical pattern of temperature change expected from increased greenhouse gases, which trap energy closer to the Earth's surface. If an increase in solar output were responsible for the recent warming trend, the vertical pattern of warming would be more uniform through the layers of the atmosphere. How do we know that the current warming trend is not caused by natural cycles? Detecting human influence on climate is complicated by the fact that there are many natural variations in temperature, precipitation, and other climate variables. These natural variations are caused by many different processes that can occur across a wide range of timescales. From a particularly warm summer or snowy winter, to changes over many millions of years. Among the most well-known short-term climate fluctuations are El Niño and La Niña, which are periods of natural warming and cooling in the tropical Pacific Ocean. Strong El Niño and La Niña are associated with significant year-to-year changes in temperature and rainfall patterns across many parts of the planet, including the United States. These events have been linked as causes of some extreme conditions, such as flooding in some regions and severe drought in other areas. Globally, temperatures tend to be higher during El Niño periods, such as 1998, and lower during La Niña periods, such as 2008. But it is clear that these natural variations are notably smaller than the 20th century warming trend. Major eruptions like that of Mount Pinatubo in 1991 expel massive amounts of particles into the stratosphere that cool the Earth. However, surface temperatures typically rebound in 2 to 5 years as the particles settle out of the atmosphere. The short-term cooling effects of large volcanic eruptions can be seen in the 20th century temperature record, as can the global temperature variations associated with strong El Niño and La Niña events. But an overall warming trend is evident. Natural climate variations can also be forced by slow orbital changes affecting how solar energy impacts the Earth climate system, as is the case with the Ice Age cycles. For the past 800,000 years, these longer-term natural cycles between ice ages and warm periods saw carbon dioxide fluctuating between around 180 parts per million at the coldest points, up to about 300 parts per million at the warmest point. Today, with carbon dioxide concentrations rising above 390 parts per million, we are overriding the natural cycle and forcing Earth's climate system into a warmer state. Attributing climate change to human activities relies on the combined assessment from observations, as well as information from climate models, to help test scientific understanding. Scientists have used these models to simulate what would have happened if humans had not modified Earth's climate during the 20th century. In other words, how global temperatures would have evolved if only natural factors were influencing the climate system, such as volcanoes, the sun, or ocean cycles. These undisturbed Earth simulations predict that in the absence of human activities, there would have been negligible warming, or even a slight cooling over the 20th century. When human greenhouse gas emissions and other activities are included in the models, the resulting surface temperatures more closely resemble the observed changes in temperature. Based on a rigorous assessment of available temperature records, climate forcing estimates, and sources of natural climate variability, scientists have concluded that there is more than a 90% chance that most of the observed global warming trend over the past 50 to 60 years can be attributed to emissions from the burning of fossil fuels and other human activities. Understanding the causes of climate change provides valuable information to help us manage our future, to find smarter, more economical, and better ways to produce the food, energy, and technologies we need to live and thrive.